Hi everyone. In this lecture, we are going to familiarize with Kirchhoff's laws and combination of resistances. Okay. So first we are going to familiarize with Kirchhoff's laws. So before going to Kirchhoff's laws, we need to know what is mean by node and what is mean by a branch. That is two terms we need to know. What is a node and what is a branch. So first we are discussing about node. Node means it is a point where two or more electric components are interconnected. So just look at this circuit here. A, the point marked A is nothing but it is a node. So here two electric components, that is one source, voltage source of 10 volt and a resistance of 5 ohm are interconnected. That is, these two electric components are interconnected at point A. So A is a node. Okay, so here two electric components are interconnected, 10 volt DC source and 5 ohm resistance. Then again B, the point B is a node where three electric components are interconnected. Which all are the three electric components? 5 ohm resistance, 4 ohm resistance and 3 ohm resistance. So B is again a node. Then the point C, consider the point C. Here two electric components are interconnected. One is 3 ohm resistance and the other is 2 ampere current source. Okay, then again D is a node where three components are interconnected. Three components are interconnected, which are the three components. One is current source, another one is voltage source, and is the resistance. So here A, B, C and D, four are nodes. Okay, then branch. What is mean by a branch? A branch is nothing but it is a conducting path between two nodes. Okay, it is a conducting path between two nodes. So between the nodes A and B, 5 ohm resistance, it can be considered as a branch. Then between two nodes B and C, there is a branch of 3 ohm resistance. So it can be considered as a branch. Then again in between B and D, there is a branch of 4 ohm resistance. Then again C and D, between C and D, the branch consists of a 2 ampere current source, like that. Okay, so that is meant by a branch. So before going to Kirchhoff's laws, you should aware about these two terms. What is meant by a node and what is meant by a branch. So then next we are going to Kirchhoff's laws. There are two Kirchhoff's laws. Okay, Kirchhoff's current law and Kirchhoff's voltage law. Okay, these two laws you might study it in +2. Okay, +2 standard. Anyway, first we are going to discuss about Kirchhoff's current law, or it is its short form is KCL, Kirchhoff's current law, KCL. Okay, so KCL states that at any instant of time, the algebraic sum of currents at a node is 0. So node, where we have already discussed what is meant by a node. So it is a point where two or more electric components are interconnected. So the algebraic KCL states that the algebraic sum of currents meeting at a node should be 0. Okay, mathematically we can written as sigma n ranging from 1 to n, capital N, In equal to 0, where capital N is the number of branches that connected to the node. Okay, that is number of branches meeting at that node, particular node, will be taken as n. Okay, then I small n is the amount of current at nth branch. Okay, so the algebraic sum of currents meeting at a node, or algebraic sum of currents at a node, is 0 at any instant of time. That is stated by Kirchhoff's law, Kirchhoff's current law. Okay, so algebraic sum means we need to take or consider the direction of currents. Okay, that is mean by by that word algebraic. Okay, algebraic sum means we need to consider the direction of the current also. That is, we need to consider the sign, plus or minus. Okay, anyway, by analyzing this law, if we have this a branch, a node like this, 4 currents meeting at this particular node. I1, I2, I3 and I4 are the 4 currents at this particular node. Okay, so how we can take the direction, or how we can select the current is plus or minus. Okay, so according to this condition, we can put the sign as plus or minus. Okay, so current flowing into the node is taken as generally positive. That is, the currents entering to this node is taken as positive. Okay, current flowing into the node or current entering into the node is taken as positive, and current leaving from the node is taken as negative. So these currents are positive and these currents are taken as negative. The current flowing out of the node, or current flowing out of the node, or current flowing out from the node is taken as negative. Okay, so in this figure, in this case, I1 is entering into the node. The current I1 is entering into the node, so I1 should be taken as positive. Then I2 is again entering into the node, so I2 is positive. Then I3 is leaving from the node. I3, current I3 is leaving from the node or flowing out of the node. So I3 is negative, again I4 is flowing out of the node. So I4 is negative. So I1 and I2 are positive, and I3 and I4 should be negative. So according to KCL, we can written as plus I1 plus I2 minus I3, because I3 is flowing out of the node, minus I3 minus I4 should be equal to 0. Okay, so this is the condition according to this node, this particular node. Okay, so again this can be written as I3 and I4 are taking to the opposite side of equals, so it become I1 plus I2 equals I3 plus I4. So again we can say that sum of incoming currents is equal to sum of outgoing currents. That is, I1 plus I2 equal to I3 plus I4. Here I1 and I2 are the incoming currents, and I3 and I4 are outgoing currents. So according to this equation, we can written as sum of incoming currents should be equal to sum of outgoing currents. Okay, so this is what is meant by KCL, or Kirchhoff's current law. Okay, then next we are going to deal with Kirchhoff's voltage law, or KVL. What is meant by KVL? KVL states that the algebraic sum, this is not SOME, SUM. Okay, this is SUM. This is a mistake. It states that the algebraic sum of voltages around a closed path at any instant of time will be 0. That is, the algebraic sum of voltages, that is mean by Kirchhoff's voltage law. Algebraic sum of voltages around a closed path will be 0. Okay, if we are having any closed path, the algebraic sum of voltages around that closed path should be 0. Okay, and then mathematically we can written as like this: sigma n ranging from 1 to n, Vn is equal to 0. The capital N is the number of voltages in the loop. Okay, so algebraic sum of voltages around a closed path will be 0. So that closed path can be consisting of resistances or passive components, as well as battery voltage sources. So algebraic sum of all the voltages around a closed path will be 0, even though it is voltage drop across the resistance, or it can be EMF across the battery or voltage source. Anyway, algebraic sum of voltages around a closed path at any instant of time will be 0. So, if we are considering a circuit like this, okay, a closed path like this, here there are two voltage sources, E1 and E2, then three resistors, R1, R2 and R3. So it is nothing but it is a closed path. So according to Kirchhoff's voltage law, sum of voltages, algebraic sum of voltages around this closed path will be 0. So it is a closed path, so algebraic sum of voltages will be 0. So here the voltage across this battery, voltage drop across this resistance, voltage drop across this resistance, and voltage drop across this resistance. Algebraic sum of these all voltages will give 0. That is meant by KVL. So here also algebraic word is there. That means we need to consider the sign. Okay. So voltage. How we can select or how we can identify the sign of voltages? Is it positive or negative? How we can identify? So here says how we need to put the sign for these voltages. So if it is a battery or voltage source, how we can put the sign plus or minus? So here first here rise in voltage. Okay, if a battery source is there, so its negative terminal is this and positive terminal is this. Okay, so if we are analyzing like this, that is if we are moving around this closed path in this direction, so we are moving from minus terminal to plus terminal, we are moving from negative terminal to positive terminal. That is, if we are moving from the negative terminal of a battery to the positive terminal, there will be a rise in voltage. Okay, negative terminal to positive terminal. As we are moving from negative terminal to positive terminal, which means a rise in voltage, right? Okay, so when there is a rise in voltage, it should be taken as plus. So plus E. Then consider this case. Here this is plus terminal and this is minus terminal. We are analyzing the circuit in this direction. So in this direction, while we are moving from plus terminal to minus terminal. That is, plus to minus means there is a fall in voltage. Plus to minus means fall in voltage. So this should be minus E. This is how we can fix the sign of EMF or battery voltage source. Then how we can fix a sign of voltage across resistance or voltage drop across resistance. Voltage drop across resistance is nothing but it is again called IR drop. It is because current into that resistance will give the voltage drop across that resistance. That's why the voltage drop across a resistance is called IR drop. Okay, anyway, voltage drop across resistance. How we can fix the sign of voltage drop across resistance. So here uh, this is the plus and this is the minus. How we can fix the plus and minus for a resistance? It is how if current is flowing, if it is a resistance and current is flowing in this direction, then current entering terminal of a resistor should be treated as positive and current leaving terminal should be treated as negative. This is the rule that you should remember. Always you should remember, or you always keep in mind that if it is a resistance and a current is flowing in this direction, the current entering terminal of resistance should be positive and current leaving terminal should be negative. This is how we need to fix plus and minus for a resistance. Then it is the plus and it is the minus terminal, and we are analyzing the circuit in this direction. Then here we are moving from plus to minus. Okay, that is when we are moving from plus to minus, there should be a drop in voltage. We have already told here we are moving from plus to minus, there should be a drop in voltage. So this voltage drop should be taken as negative. Then again it is a resistance, current is flowing in this direction, so current entering terminal will be positive and current leaving terminal should be negative, and we are analyzing the circuit in this direction. So we are moving from negative terminal to positive terminal. That means there is a rise in voltage. So that voltage drop should be taken as positive. That is explained here. Okay. So this you should keep in mind how a EMF, sign of EMF can be fixed and sign of voltage drop across resistance can be fixed. So if we are considering this circuit, here 2 voltage sources are there and 3 resistors are there. First we need to fix the direction of current. Okay, this is the first procedure. We need to put the direction of current. Commonly we will always put the direction of current in clockwise direction. It is a closed path, so we will fix the direction of current in clockwise direction. So if it is the current path clockwise, current direction is in clockwise, then mark the plus and minus terminals of resistors. So for R1 this is plus, this terminal will be minus. For R2 this terminal will be plus, this terminal will be minus. Then for R3 this terminal will be plus, this terminal will be minus, because current flow is in this direction. So current entering point will be plus, current leaving end will be minus. Then for voltage sources there should be signs, plus and minus terminals should be marked, already marked for voltage sources. So no need to mark the plus and minus terminals for voltage sources. So the first procedure is mark the plus and minus terminals. Okay, so first procedure, mark the direction of current in clockwise direction, then mark the plus and minus terminals for resistors, then apply Kirchhoff's law, Kirchhoff's voltage law. So according to Kirchhoff's voltage law, voltage E1, we are analyze the circuit like this, in this direction itself. So E1, as we are moving like this, we are moving from minus terminal to plus terminal in E1. Through E1 we are moving from minus to plus. So E1 should be plus, that is written here. Then voltage drop across resistance R1 is taken as V1. So as we are moving from plus to minus, there is a drop in voltage. So V1 should be negative. So it is negative, minus V1. Then again V2, we are moving from plus to minus. So again it should be negative. Then for E2 we are moving from as we are moving like this, we are moving from plus to minus again, so it should be again minus. So E2 again should be minus. Then V3 again we are moving from plus to minus, so there is a drop in voltage, so minus, again minus V3. So only E1 is plus, all other voltages are minus. So it can be written as plus E1, okay, plus E1, then minus V1 minus V2 minus E2 minus V3 equal to 0 according to KVL. Then again it can be written as voltage drop across resistance R1 can be written as I into R1 if I is the current flowing through the resistance. So all the voltage drops across resistors are replaced with I into that corresponding resistance. Okay, that is the last equation. E1 minus I into R1 minus I into R2 minus E2 minus I into R3 is equal to 0. So this is nothing but KVL. Okay, then next is combination of resistances. So resistances can be connected in series as well as parallel, or combination of series and parallel. Okay, anyway, series connection of resistances means the one end of the resistance is connected to the other end of resistance, and its other end is connected to the another end of and one end of another resistance, and like this. That is the circuit in which resistances are connected end to end, so that there is only one path for current flow. Okay, that is called series connection. So the series connection is shown in figure. So here in series connection we should know that the current flowing through all the resistors should be same, and voltage drop across the resistances will be different, and it will be given by Ohm's law. That is, current into resistance will give the voltage drop across each resistance, but the current flowing through all the resistors should be same in series connection. Okay, then next is how we can find out the total resistance or equivalent resistance of a series combination. So this is the proof for finding out the total resistance of a series combination. So here according to, if we are applying KVL here, we know that algebraic sum of voltages around a closed path will be 0. So it is a closed path, so voltage sum of voltages should be 0. So here first we need to mark the assume the direction of current. So we are taking this is the direction of current. So then mark the positive and negative terminals of resistors. So for R1 this is plus and minus, for R2 this is plus and minus, and for R3 this is plus and minus. So as we are moving through this closed path, here we are moving from minus terminal to plus terminal, so plus Vs. Then all other cases we are moving from plus to minus, so all that voltage drops should be minus. So Vs minus V1 minus V2 minus V3 should be equal to 0, or again we can written as Vs is equal to V1 plus V2 plus V3. Then again V1, V2, V3 are replaced with current into corresponding resistance. So I into R1 plus I into R2 plus I into R3. So I is common, so we are taking that outside. So I into R1 plus R2 plus R3. If we are replacing this circuit or this series combination with an equivalent resistance called R, this will be the circuit. So these three resistors are replaced with this R. So for this circuit, what will be the total resistance R? V divided by I. Voltage divided by current will give resistance. So here in this circuit, R will be equal to V divided by I. So Vs divided by I. This is Vs, voltage is Vs. Vs divided by I. So from this equation, if we are taking I to this side, here become Vs divided by I. So Vs divided by I is equal to R1 plus R2 plus R3, but we know that Vs divided by I is nothing but the total resistance of the circuit or equivalent resistance of the circuit. So for series connection, equivalent resistance can be given by the sum of all the resistances connected in series. Okay, so commonly we can say that if n resistors are connected in series with resistances R1, R2, R3, etc. Rn, then the total resistance of that combination can be given by the sum of all those resistors. Okay, then next is parallel combination. What is meant by parallel combination? Parallel combination means one end of all resistors are connected to a common point and another end of all that resistors are connected to another common point. So such connection is called parallel connection. The circuit is shown in figure. So from this or here, we need to know that the voltage across all the resistors should be same. So in parallel connection, voltage across all the resistors should be same, but current flowing through each resistance will be different. Okay, so in parallel connection, current will be different, voltage across the resistors will be equal. In series connection, current will be equal and voltage drops will be different. Okay, then next is how we can find out the equivalent resistance of such a connection. So here we need to apply KCL at the node. At which node? Here. This is a node. Okay, so at this node we will apply Kirchhoff's current law. So Kirchhoff's current law says that algebraic sum of currents at a node will be 0. So here, or we can say that sum of entering currents will be equal to sum of outgoing currents. So according to Kirchhoff's law, we can written as I is equal to I1 plus I2 plus I3. I is equal to I1 plus I2 plus I3. So I1 is nothing but voltage across the resistance divided by resistance. Okay, current I is equal to V divided by R. So voltage across R1. I1 is the current flowing through the resistance R1. So I1 will be equal to the voltage across the resistance R1. Voltage across the resistance is nothing but it is Vs. By analyzing the circuit, we can show that R is connected actually parallel to this Vs. So voltage across R1 is nothing but this supply voltage itself. So I1 equal to Vs divided by R1. So that is like this. Then I2 is nothing but Vs divided by R2 and I3 is nothing but voltage Vs divided by R3. Then Vs is common, so Vs we are taking out, we will get like this. So Vs is taking to this side, we will get I divided by Vs is equal to 1 by R1 plus 1 by R2 plus 1 by R3. I divided by Vs is nothing but 1 divided by R. We know that Vs by I is equal to R in this circuit. So I divided by Vs will be equal to 1 by R. So 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So by using this equation we can find the equivalent resistance for a parallel combination. Okay. So generally if n resistors are connected in parallel, then we can written as 1 by R is equal to 1 by R1 plus 1 by R2 plus etc plus 1 by Rn. Okay, generally if two resistors are connected in parallel, R1 and R2 are connected in parallel, we can written as 1 by R is equal to 1 by R1 plus 1 by R2. If we are cross multiplying this, we will get 1 by R is equal to R2 plus R1 by R1 R2, or R is equal to reciprocal. Okay, equivalent resistance R is equal to R1 R2 divided by R1 plus R2. That is, if two resistors are connected in parallel, then the equivalent resistance will be R1 R2 divided by R1 plus R2. So this equation you need to by heart. If two resistors are connected in parallel, equivalent resistance will be R1 R2 divided by R1 plus R2. If two resistors are connected in series, equivalent resistance will be R1 plus R2. Okay, so this is all about this presentation. Thank you.